Okay, cool. So I'll start. So to begin with, I think Aditya wrote me an email sometime back, and he wanted me to give a talk, and I wanted to actually understand what kind of a talk I would have liked to, let's say, listen to if I was given an option when I was in my second year, third year. So I'm a 2007, 2012 batch, so way back in 2008, 2009, when most of you were in school. So one talk that I would actually have liked to listen to is what is an experimentalist basically, and why. I mean, we hear these terms, theoreticians, experimentalists, to begin with, and then we get confused when we are in second year, third year, 20-year, 21-year old, and then we start a journey, and then we really don't know how to process the thing. So I wanted to give a talk of how to be a bad experimentalist. So the thing is very simple. You have a universal set, and you know how to be a bad experimentalist. You subtract that, and then you know how to be a good experimentalist. That's my basic concept of this talk. But this topic is more of, as you would understand, a gimmick to attract more participants, to be honest. My talk would basically be how to be a good experimentalist, but I would also tell you what things you should do and not do to at least begin. But before I begin, I'll tell a disclaimer that my talk is just a guiding point. It's not going to be a book that you should refer to, and then you judge your career and you judge your personal abilities and things like that. What you can do after this talk, you can interact with me. I can help you understand things. We can just discuss. So let's begin in this journey. So yeah, as I mentioned, forget the title. So I'll just tell you a few prerequisites of a basic experimentalist, and two very common words that you always hear, which are acumen and temperament of an experimentalist. And then we can discuss a few things about how an experimentalist really becomes an experimentalist, or what, or how a person works in a lab. And then we go to the obvious topic: where do you work? And of course, it's going to be experiment, experiment, experiment. A lot of my friends are like, they don't like experiments at all. So it's a joke. Please don't sign off. Please bear with us, and maybe I can convince you to become an experimentalist by the end of the talk. So to be very short, I have a very few slides because I want more of a question and answer session. I want you to ask me many questions, and I want to answer many questions of yours. So let's start with prerequisites. So I think a physicist in general, or a scientist in general, is a very a gender neutral, age neutral, race neutral concept. You can never be a black or a white scientist. You can never be an old or a young scientist, a male or a female scientist. You can either be a scientist or you cannot be a scientist. And this becomes very specific when it comes to especially being an experimentalist. And that's why I don't say who is an experimentalist. I say what is an experimentalist. So and don't get this concept wrong that to do an experiment you must enter a lab. For example, if you go to your if you go to your scooty and your bike, if you press that self start and the bike just starts on its own, if you stop and think, why did this happen? If you go home and you Google it, how does a self start work? You are actually an experimentalist. If you just look at an inverted rainbow, after you take a selfie, you just maybe go and see how is an inverted rainbow formed. What's the difference between a normal rainbow and an inverted rainbow? You can actually call yourself an experimentalist, and so forth and so on. So you can see I've written X-rays, radioactivity, penicillin, and you can think, and there is a link. There is a very common link between these three rather phenomenon, I would say, not penicillin, but the common link is these three were completely accidental discoveries. If you read about X-rays, William Röntgen, radioactivity, Henri Becquerel, and penicillin, Alexander Fleming, if you read about them, and if you read about these three phenomena, they are completely accidental discoveries. But so my entire the next 10-15 minutes I'll talk to you will be completely based on these three discoveries and how accidental experimentalists come to be, and how it can actually get you a Nobel Prize in all the three cases actually. So these three cases, X-rays, I'll just give you a short story actually. Röntgen was not actually looking to discover X-rays. He was actually working with cathode ray tubes, and he had covered the cathode ray tubes with a black cloth. And then he saw that a photographic plate in his lab was actually glowing. So he thought, well, I don't know what it is. So he said it's an unknown ray which is penetrative enough to cross this thick black cloth and imprint on a photographic plate. So he says it's an unknown radiation. So he named it X-ray. Now, this was in the late 1890s, so 1880s, 1890s. And then soon after this discovery, Henry Becquerel, so William Röntgen was in Germany and Becquerel was in France. And Becquerel came from a family of physicists. His grandfather, his father, both were chairs of the Physics Society in France. And then he read the paper about X-rays, and then he started thinking, because he was an expert in phosphorescence and fluorescence. So he thought maybe I can link these X-rays to my research. And then what he did is he took some photographic plates, he covered them with thick black cloths, and then he put uranium salts on these. And then he put it out in the sun so that the uranium salts could absorb the sun ray and then give out X-rays. And then he wanted to see if these X-ray images were found on the photographic plate. As obvious, they were formed. So he was happy. He was like, okay, uranium is absorbing the sunlight and giving out X-rays. And he went home, he put his photographic plate, uranium salts and everything in a drawer. He went home and he came back and he saw that, wow, even without proper sun ray, he could actually see very nice imprints of these uranium salts and other materials he had kept. So he thought maybe let's do more experiments, and he wanted to keep them out in the sun ray again. But France being France and Paris being Paris, he did not find a sunny day in the next week or something, and he had a conference coming up. So he said, I'll just keep it anyway, and then I'll see. And to his surprise, he still saw those implants, those imprints on the photographic plate, even without any sun rays. So he started theorizing. He said, maybe it doesn't actually absorb sunlight and give out X-ray. Maybe it's just giving out light itself. And rest is history. A few years later, Marie Curie, her husband, they all started working on it. They coined the term radioactivity. They found thorium, plutonium, polonium, other many radioactive elements, and this came to be. The third thing, penicillin, was same. So Alexander Fleming was actually a biologist, a virologist to be exact. And then he did similar things. He went on a holiday. He kept many petri dishes before going on a holiday. And he came back and he saw that, there was a particular kind of bacteria, I think it was a bacteria. I'm not a biologist, so I don't know exactly, but he saw that in all the petri dishes, there is an absolute growth of bacteria other than one, where there is a mold. Mold is that kind of a bread mold that occurs when you could keep bread out for a long time. He saw that there was no growth of bacteria in that petri dish in and around that particular mold, as if that mold had secreted some chemical or something to avoid this growth. And then he told his lab assistants to isolate this penicillin notatum genus, and then isolate it and use it for antibacterial applications. And then we have cough syrup, everything basically. And that was the beginning of medicine basically. So the thing to tell you about is, it was not like they were walking in a park and suddenly they discovered X-rays, or they suddenly discovered radioactivity, or they suddenly chanced upon penicillin. They were actually working. They were actually working very nicely in the lab. They were actually working full days and nights in the lab. And then, they chanced upon these. So ideas always come to a ready mind. You cannot just sit on your couch and expect yourself to be hit by an idea. It doesn't happen. It happens extremely rare. So not just in your lab, in your general life, you should observe. You should observe everything. You should be a sponge basically for knowledge. You should observe everything and you should infer. If this is happening, what's happening? Why is it happening? Why is it happening? What not? So the two terms that we generally chance upon a lot of times are experimental acumen and scientific temperament. So these are dictionary terms. You can look up in the dictionary, but when you come to the lab, it's basically your ability to spot a solution and your ability to extract that solution. And there is no magic to this. Well, you can say some people are born with a good experimental temperament or a good experimental acumen, but That's not true all the time. You can, even if you're not born with it, I mean, nobody knows what we are born with, what talents we are born with or not, right? So even if you're not born with it, you can develop it. You can culture it, you can nurture it, you can practice and practice and practice, and then you can actually become good at something that you want to do and that you like to do, basically. So don't be afraid if you're not good at experiments at this stage in life. Nobody is at your stage. Trust me. There are many experimentalists who at 50 years of age or something maybe switched on to theoretical physics and vice versa, because they just discovered this talent in them and they wanted to explore because it really interested them. So you have to practice, and practice happens when you actually work and go to your lab, do stuff, and you have to take calculated, educated risks in the lab as well. Now, risks doesn't mean that you play with the instruments and you push the instruments off the table and see whether it breaks or not. No, that's not it. You have to take calculated, educated risks with the knowledge that you have. You have to see what is going on. If you're given a manual to read, and if you're doing an experiment in the following 3 hours coming, you should see what is happening. You should take risks in the sense that you should push yourself to some limit. And of course, if you become an experimentalist, you must fail, because if you're not failing, then you're doing things very much by the book, and you can never become a brilliant experimentalist if you always follow the book. That's for sure. That's one I can tell you. But more on this further later. So how, basically, as I just mentioned. So let's take a simple example. What I have gone through in 5 years with faculty members like Rai sir, Vipul sir, Sani sir, Pathak sir, and what you guys will also go through. You get a manual. You know what experiments you have to do. You know what the aim of the experiment is. You have to basically understand. What we tend to do, what the mistakes that I have done that you should not do, is we read and we try to just somehow perform it and then finish those 3 hours and go to chat with our friends and things like that. You can do that, but 1% of you will not do that. 1% students among you will actually read, and I want that 1% to increase and become 90% probably. You have to read what is there in the manual, and you have to ask questions. You have ample resources. You have your internet on your phone. Instead of, I mean, you can spend time on Instagram, but you can also just Google things. If there is something which you think you need to read more, understand more before going to the experimental lab, just Google it. You have to ask, how is this particular thing happening? If you do a double slit experiment, if you just take a simple prism, and if you see a white light diffracting, you have to understand, why is it happening? Is there an alternate? Can this thing that is happening be replaced? Because if when you ask these questions, you will see that you're pushing your knowledge level to a higher level, and it has got nothing to do with the experiment, as I mentioned to begin with. It's your scooty, it's your bike. You press the cell start, your bike starts. You have to ask, "Ye kya hua? Why did it start? Why don't I have to push that kicker anymore? If that kicker takes so much mechanical energy, how does just a push of a button do that entire conversion?" These little things, so you have to understand. And you have to, of course, understand the nitty-gritties, because nitty-gritties are very important at your level, especially because these are your formative years, these 19 to 24, 23 years of age. You have to actually develop your acumen and temperament at this stage. You have to become a sponge rather at this time. If you are if you're carefree at this point in time, that okay, it's happening, I don't care how it's happening, it's just happening. Sir ne bola kar do, sir ne bola ye bola, we'll just do it. If you just follow steps that your faculty members tell you, then you will get your experiments done, you will get the grades, you will get everything, you will pass 5 years, but then you will not enjoy it. When you start understanding the nuances of techniques, that's when actually you start enjoying an experiment. And when you actually enjoy an experiment, you don't want to stay 3 hours, you actually want to spend two or three more hours in the lab in the coming couple of days, maybe when nobody else is there. So you have to challenge the techniques that exist in past. Before challenging something that your faculty member tells you to do, you should be a master of what he's telling you to do or what she's telling you to do. Because until you know what you're doing, you can really not challenge that thing. It's a simple logic, basically. And it's same in the kitchen. Unless you know how to make something, you cannot develop it. It's as simple as that. And you have to think out of the box. You have to be imaginative. You have to be creative. And this happens everywhere. Again, trust me, experimentalists don't exist just inside labs. They exist everywhere. So you have to be creative. You have to push your boundaries. You have to increase your mental faculty, and you have to do things which nobody else thinks of doing, basically. Well, well, I'm a cricket fan, and Saurav Ganguly used to say one thing that nobody ever became a cricketer by sitting in the dressing room. So he would push up people like Dhoni and Sehwag to open the cricket, open their batting. Similarly, it's an experimentalist. You can never become an experimentalist by sitting in a classroom and looking at other people perform. You can never become a good experimentalist if if you see some faculty member performing the experiment or your research associates performing the experiments and you're just standing behind and you say, okay, I have understood how to do it, and then you go and write your journal and go back. No, if you have understood, you have to do it. You have to actually get down and get your hands dirty. You have to actually hold that soldering gun and try to solder something, burn your finger, and then you have to see how that solder wire smells, and then that's the only time you actually feel that you're an experimentalist. And unless you feel you're an experimentalist, you can never be an experimentalist. It's as simple as that. So you cannot be afraid. You cannot. So that's what risk taking is. You cannot think that nobody in my batch is doing it, so I should not do it. You should do it if you like to do it. And my experience over the last 13 years with my department is our faculty members are extremely supportive. If you want to go from A to B, they will help you to go from C to G. So you have to show interest, and then everything is available to you. Work when nobody else works. This is very important. Generally, what happens is your lab will be filled with 30, 35 students on an average. And it's very difficult. When you're working in batches, you have a batch of 3 students, and then everything goes very quickly. No? So if you really want to understand how an experiment works, first you have to understand what an experiment is, and then you have to understand how the experiment works before you can actually question why it's working. So you have to come when nobody else is there. You have to sit, you have to think, you have to do. You have to, as I said, you don't wear a watch to the lab. If you wear a watch to the lab, then it's a waste, basically. You have to free up your mind. You have to sit in your lab. You have to see how the experiments are working, what is happening, why is it happening, can I improve it, can I do it in a faster way, can I do it in a smarter way, can I do it in a very economic way if it's something that uh, involves in programming, basically. If I tell you to write a set of program, 5 of you will write it in 5 different ways. So you have to ask, how can I make it faster? How can I make it better? And you have to also discuss. So one advantage we had was we were an ASHD department, Applied Sciences and Humanities, and we had chemistry and math students. We were in very close physical proximity to these students, so we could discuss what is going on in the lab and what is happening in our lab if you want to. So once I passed out, I actually saw this is extremely important because physics is a lot about chemistry, and if you have worked, you know it's a lot about mathematics as well. So you can just not be a good physicist. It's impossible. You have to have some knowledge of chemistry and a working knowledge of mathematics to be a very good experimentalist, especially things like trigonometry, geometry, basic things like that. So you have to discuss interdisciplinary ideas because you might see that your experiment might not be working and you're not able to understand probably. But if you discuss with your friends, you their field, their experiments might actually help you understand your experiment. Now, the last point is very important is you have to revisit history. So while I was preparing this talk, I actually wanted to go and read how did Becquerel, Roentgen, and Fleming actually chance upon radioactivity, X-rays, and penicillin respectively. It's a beautiful, interesting read. You have to see how Raman did his work. You have to see how Einstein did his work, how Galileo did their work. So these things were, well, Einstein basically was not a pure experimentalist, but you could actually go and read Newton, and you would see he had so many crazy ideas in his head, very, very crazy ideas. You have to revisit history because we have actually forgotten a lot of techniques which they used, and they are extremely, extremely out of the world techniques. They will sound very new to you, but they were done 300 years before you were born. So you have to read a lot out of interest. Don't do it for getting marks or for writing a project or something. Just read it out of interest. So you have to be in a lab to be an experimentalist, and you can be an experimentalist out in the world as well. It's as simple as that. So that's it. That's my talk. I wanted to keep it very short because I want you to ask me things now. I want to know what things you want to do, what things you want to know, how a nuclear experimentalist works, what doesn't work, what works, everything. So I'll give the stage back to you. I'll stop sharing my screen if you want.
The participants can either write their doubts and questions or whatever they want to in the chat box, or you're free to unmute yourself and ask. Now is the time to ask. You won't get this opportunity again. So I highly request everybody to get their whatever is there in their heads clear.
Oh yeah, I need to ask something. Okay.
Sure.
So do experimentalists get influenced by the theory?
Absolutely. So I think I was talking with Deepak, or I don't know whether I was talking to you about simulations and things like that. So very honestly speaking, there is a very thin line between there is a very fine line between an experimentalist and a theoretician. You cannot be. This is I can speak from the nuclear physics perspective. You cannot be one without being the other. Very nicely. So if you're a theoretician, if you're developing a theory, you need to actually know how an experiment works, because you can give me unrealistic as a theoretician you can give me unrealistic energies required to form a particle, for example, but that's not possible in an experimental lab. So a theoretician needs to have discussions. He doesn't need to be an experimentalist, but he needs to have discussions. He needs to influence his theories by experiments, and it works the other way around. So if you're an experimentalist, you have to also understand how what's the theory expecting. For example, we work in the energy range of electron volts to giga electron volts, and if I don't know where to look, how do I look? So a theoretician influences my experimental techniques. He tells me, okay, you have to use these kind of detectors if you want to actually look in this kind of energy region. Now, how to make that detector? What kind of whether it needs to be a solid state detector, it needs semiconductor detector, it needs to be some solar thin films on something. That depends on me, but of course, the theoretician has to help me understanding where to look for the needle in the haystack. So they are very much interdisciplinary, but yeah, it's very difficult for an experimentalist to be an expert theoretician. Don't try doing that. This is one big mistake that we do. We try to be a jack of all, and then we end up being nothing. So you have to know that what do you want to be. If you want to be an experimentalist, you have to have a fair idea of theory. You don't need to be an expert in theories. And if you want to be a theoretician, you need to have a fair idea of experiments. You don't need to be an expert of experiments. So the short answer is yes, it does influence.
So, like, I have something, I have a disagreement over your point,
Uh-huh.
because what I personally would feel is like, if you get influenced by theory, then the research outputs, whatever you give, will be a bit biased towards the theory, right? So, uh,
Uh-huh.
will because like experiment theory is far ahead than the experiments in
Uh-huh.
everyday research. Yeah, so. Uh, like what I personally felt is like because of since theory is far more, experiments are going to prove those theories. Okay, and they get biased with the theories and they try to prove what theory has said is true. So
Uh-huh.
yeah, so this is what I felt like. Do
That's
they
a that's
work
a
independently?
Yeah, that's a good point. So no, they cannot act. They can never actually work independently. That's true, because what you said is very right. Theory is way ahead, but I can give you a few examples of the work we do in GSI itself in nuclear physics. We have disproven 30-year-old theories, basically. So we actually were trying to do what you mentioned. We were trying to prove a theory. So there was, suppose, an isomeric state in some nucleus predicted 30 years back, and they said, if you do this, you will find an isomer. We did that. We did not find an isomer. And then the experimental brain came in, and we said, okay, let's do our thing and let's see if it's somewhere here and there. And we did something of our own, and we saw that actually the theoretical predictions were completely off charts. And we actually said that, okay, this is the particular energy, or this is the particular domain where you want to, where you can actually find these. And we found it. So the theoreticians had to sit down and modify 30-year-old theories, basically. So, and the same goes for a theory. You can just not you can just not do experiments on computers. You can run simulations, you can run models, because models experiments are model dependent in terms of theory, and you can have n number of models. You can put a neutron, you can take a neutron, you can pull a proton out, you can put a proton in. You can do whatever you want to do in a computer, but you have to prove it in a lab, because a lab is the place where nature manifests itself. And nature doesn't show its true face on your computer. No, nature will show its true face on your detectors. So when you say influence, I don't want you to get influenced in the way that you restrict yourself or you change your experimental ideas according to theory. But most of the times what we see is the theoreticians are very much within the ballpark. They're not very wrong. So you can use them as a guideline rather, not particularly as a book that okay, the theoretician has told me to do this, so I should do this. No, but you can get hints that okay, this is the ballpark where I should be looking for this particular phenomenon. Let's try. But you should also be inventive in that. You can actually be inventive in the way you can do more than what the theory has predicted. And as I told you, my personal experience, you can disprove 30-year-old theories which were influencing textbooks and everything. So they go hand in hand, unfortunately, but that's the way it is.
Yeah, and one last question from my side is like you have said about Fleming's invention on
Mhm.
penicillin, Curie's invention, Becquerel's invention on radioactivity. So those
Mhm.
were highly useful to the human society. So, like, can you say like in the past 2 decades, whether these experiments are useful to the human society?
Well, firstly, these were all discoveries. So discoveries are always interesting because it basically punches you on your face and tells you that it was there all the time. So we lost millions of human lives before penicillin was actually discovered by Fleming. And once it was discovered, we found antibiotics, and we are down to 5% unless coronavirus hit, of course. What is happening in the last 2 to 3 decades is basically development. So if you look at I'll just give you one example. If you look at solar cells, if you look at solar cells of 1980s, and if you look at solar cells of 2020 or 2019, 2018, you will see a huge improvement in efficiencies. And what this is doing is this is taking us towards a greener Earth. So in 1980s, there was actually no possibility other than using fossil fuels. We were hugely dependent on coal. We were hugely dependent on petroleum, and that was not just financial or political. It was scientific because we couldn't use solar cells in 1980 due to the very low quantum efficiency. It's as simple as that. In the last 2 decades, what has happened is the quantum efficiency has increased manifold, and now we can actually, there are countries, there are cities in Germany, and there are cities in India also which are coming up, which are completely off fossil fuel and dependent on renewable sources. So there are many inventions which are happening, but it's not fair to call them inventions because the inventions have happened. We are developing things because right now the 21st century is mostly about development. You are developing things which are already known to you. You're making them better. You look at SpaceX. What is it? We were sending men to moon in the 1970s, 1980s. But what did SpaceX do? What it did is it sent a rocket, and it brought that rocket back. 30 years back, it was impossible. 20 years back, it was impossible. If you told a NASA scientist that you could have reusable rockets, he would laugh. He would tell you to get out of his office. But now they have done it. So these are little things. So this gives us hope. I mean, we say everything has been done, all inventions are over, all discoveries are over, but actually not. Invention and discoveries, the macro things are maybe they are done, maybe, but development has, we have not even scratched the surface of development. There are so many things we are developing. We have to develop. You just look at Corona. It was a punch in our guts. We did not even have proper vaccines. We thought we were very advanced. We had discovered penicillin almost 100 years back, but it took us so long to tackle this virus. So there's a lot to do. So maybe not inventions or discoveries like an apple falling on your head, maybe that not, but development for sure. We have not even done even 10% of what we should do or what there is left to be done. This is my personal prediction.
Yeah, that's it from my side. Thank you. Yeah.
Yeah.
Sir,
Yes.
so what in your life as your profession, what is your daily life and what is your excitement when you wake up upon waking?
That's a very good question. Thanks, Mohit. So, well, one thing, uh, one thing is experimentalists don't live their life differently. The biggest motivation for me to wake up is that I'm hungry or I'm thirsty. Is as fact as that. I want to have breakfast, very frankly. But I know what you want to ask. You want to ask what makes me live to go to the office, and I'll tell you a very simple thing. My working style, and most of the experimentalists in my field in Germany work in this way. We do such exciting work the evening before we go to sleep that next morning we don't need to find that motivation. We just it's a momentum. So in very short, so it's very simple. I'm a late riser. I don't wake up early, and my faculty members are a proof. I had two subjects degraded because I used to miss my 8:30 a.m. classes all the time. I couldn't ever wake up before 9, and it has remained the same. So what I've done is I stay up late. So I have modulated myself. So as a normal experimentalist, you have to work long hours in the lab. Now there are two kinds of people. There are two kinds basically. You either wake up early, you run to the lab, and before people start coming in, before there is this noise and there is this chit chat going on, you do as much work as you want. Personally speaking, I like working late in the evening. So I go to my office at normal 10 a.m., 10:30 a.m. or something. I check my emails, I do my regular stuff, and then I actually don't go to the lab until lunch. Because one thing I've personally observed is if you go too much in the lab, you lose that hunger. You lose that, let's say, that craze to work in the lab. It becomes something like, okay, I can go anytime. So what I do is I try to stop myself going to the lab until lunch. And then after my lunch, I actually go to the lab. And then once I'm in the lab, I actually leave my phone back in the office while going to the lab. So if I'm in the lab, I'm in the lab. It is as simple as that for me. And unless I feel that, okay, there are many days, as this might happen with everybody. You might have also faced it. There are days when I don't want to go to the lab. I just don't want to work in the lab, and I don't go because I know if I force myself to go to the lab, I will not do any progress. I will just be sitting in the lab doing some rubbish, and then I will not. What will happen is I'll lose my interest. So it's absolutely fair not to work at times. At your age, at my age, we all try to push ourselves, but this is not true. At times, you should actually take time off. You should just forget you're working. You should feel free. You should be happy in what you do. Unless and until you feel like you have to go to the lab, you should not go to the lab. And this is the way I work, and this is the way most of our people work in Germany. And I dare say we make very good progress because when we are in the lab, we are in the lab. So there is no fixed hour, there is no fixed routine. There are days when I have to stay a couple of days at a stretch without coming back home. I have to stay in the lab before setting an experiment. And there are weeks when I don't go to the lab because there's just nothing new to be done. There is nothing exciting happening. So then I do theoretical analysis. I run different simulations. I run different codes. I try to design new experiments, but I don't even go to the lab. So I don't know if that answered your question, Mohit.
Yeah. And one more thing, you said about the curiosity of finding things in everyday life. So, but I feel like if I am thinking about these things, they are already like most of the things are already available on net and all. So, still,
Yes.
what can be discovered or improved at my level in my age? What do you
Yes.
think about that?
So this is a very good question. Actually, again, I'll give you a very very recent example. And Elon Musk. There is nobody who has not heard of him. So he had this exact doubt that you're having. What should I discover? What's the next big thing? Basically, what's the next big thing that that needs to be discovered so that I can go to the lab and I can make something I can discover. So Elon Musk went to NASA's website in the 1980s, 1990s, and he saw that for the next 30 years, NASA was not doing anything new. So, if you and I, as general people, as I would say, above average aptitude people, we look at the NASA website, we'll be like, wow, look at the nebula, look at this galaxy, we'll be lost in those things. But Elon Musk actually thought that, well, NASA is not doing anything new. They are just sending shuttles, that's bringing shuttles back. So he did something new. He said, I will make reusable rockets. So what do we learn from this? We learn that there are many things we think we know, but we don't know. For example, you just look at how a motorcycle starts by the press of a button. It's already there in the internet. You read it, and then there is a very very finite possibility that you say, wait, why are we doing it this way? Why don't we do it this way? So There is an existing technology which people have taken for granted. And remember, inventors are 0.0001% of the world's population. How many inventors do we see? The primary reason we don't see many inventors is not ability. We don't see many inventors is because we don't ask these questions. That we just take everything for granted. We are like, okay, it's a motorbike. I press a button, it starts. I go to Google, I read it. Okay, I know what's happening. But when you read it, you have to ask yourself, could I have done it better? Do I understand? First, you have to ask, do I understand this procedure perfectly? That, okay, this happens, the ignition flows from here to here, and then I start the bike. Once you have understood the method, if you remember my slides, you have to first understand what is happening. Once you have understood, you can ask yourself, can I improve it? And trust me, Mohit, if you take up 20 topics, if you give yourself 6 months and you write down 20 topics, that, okay, I will try to understand how these 20 things work. Very common things. It could be an ignition stove, how you just turn it and it sparks and it just burns. It could be very basic topics. If you do this for 6 months, these 20 things, you will see there will be at least one thing where you ask yourself, can I do it better? And what you will be doing is you will not be actually inventing something directly, but you will be preparing yourself. And as I said, agriculture happens on fertile land. What you will be doing is you will make your mind fertile to new ideas, to new concepts. So what happens when you're 35, when you see something happening, because you've prepared yourself when you were 22, you will suddenly see, wait, there will be a light bulb moment. And then you will see, wait, I can do this better. And then you will be an inventor. Then you can actually discover something new. You can actually develop something new. So you should not lose hope that there is nothing to be done, because there is a lot to be understood. And once you have understood a lot of things, then you prepare yourself to do something new. That's the procedure. Elon Musk did not become Elon Musk overnight. We read the stories, we read the Bloomberg interviews, and we hear him say, but 30 years back, he went to a website and he said, well, I will become a rocket scientist. And see what he has done today. Everything was there on Google, everything was there on Wikipedia. He could have just read it and closed the tab without any motivation. But there was a motivation he found. He invented that motivation. First, you have to invent a motivation, and only then you become an inventor. Then you become something that maybe your batchmates are not. That could be very much possible.
Thanks a lot. That makes me very excited.
Good. I'm happy.
Excuse me, sir.
Yes, Rohan?
Sir, I'm actually leaning towards theoretical physics, sir. But still, I am in first year and I don't know much of the field, so I'm here. But as a physics student, I don't think I'm spending much time. So like, I'm motivated and all, I work and all, but I don't feel I'm putting the right efforts. Like,
well, you're in first year, you said, right?
Yes, sir, first year.
Yeah, you should take it very easy. So if you enter the department, if you look at the left side on the board, you have my name. I'm not boasting, but I'll tell you.
So we can't.
I'm a triple 10 pointer. I'm a triple 10 pointer. I got 9.8 in one semester, but first year I made squash. So I don't know if you've heard of squash or not. I used to be one of the massive bunkers in first year. I mean, Rai sir, Vipul sir, these people had seen me and they would know this, but you should not push yourself too much. You should, the basic, at the end of the day, you have to enjoy what you're doing. And if you ask yourself, I think you're 18, or you would be hardly 19, I would imagine. 18, exactly. So you cannot ask yourself to push yourself, because you will exhaust yourself too early. There are things. So basically, I'll tell you this. You are basically warming up for the marathon in front of you. And if you have ever seen a marathon runner in an Olympic, he doesn't start running full speed on the very first lap. He has to run. He has to understand how his muscles are working. He has to understand how his competitors are doing. And then he goes for the sprint at the very end. What you are trying to do is you are trying to sprint at the very first lap. What will happen is you will run out of energy by the end. And this is the most dangerous thing. You will have a burnout. I keep telling my PhD students in GSI as well that I see many PhD students who work 18 hours. 18 hours. I mean, they would just take shower breaks and come back and work. I don't allow them to do that. I say, at the end of the day, you have to enjoy your life. And if you're pushing yourself too much, I mean, experimentalists, theoreticians, these things, physicists, scientists, these things come secondary. So primary is your life. If you don't enjoy doing something, you will soon have frustration, and then you will become desperate, and then you will start comparing yourself with others. You will make a mess. So first, don't become a theoretician in your first year, because I used to think I used to think I will be a very big experimentalist sometime, and I got a job in Infosys through campus placements, and I had my tickets and everything booked to Mysore, and then I happened to go to Lindau, and I spoke to many Nobel laureates, and the basic thing I understood from them is the following. So I'm just giving their knowledge to you. These are not my words. I'm just passing on the knowledge. So the basic thing that Nobel laureates say, that you have to have the hunger, and you cannot make yourself hungry. You cannot force yourself to become hungry. You have to become hungry. What you have seen, what maybe many people do is they go for a walk around the park. So they're working up an appetite basically. So you have to, at this stage, you have to work up an appetite. You have to try to become hungry. You just cannot force yourself. You cannot say, okay, Akashrup Banerjee at this stage is in GSI. I want to become like him when I'm 18. No, you just should not do that. You should not look at Ajay Rai. You should not look at Vipul Kheraj. Anybody, everybody has a unique life. If you feel you're not giving enough to the field, fine. There is no textbook. There is no textbook which tells you that, okay, anybody who comes at 9 a.m. in the lab goes at 9 p.m. is a good physicist. No, I have many friends who work half the time and give out twice the progress. Everybody is unique. So don't push yourself. Enjoy, make friends. First year is only for making friends. I mean, I'm not telling you not, I don't know if Rai sir is here, he will scold me. I'm not telling you to bunk classes. I'm not telling you to, stop going to classes, but learn to live. And once you have done that, physics will come to you, because every physicist, every good physicist is a very good human being. And you can be an awkward, you can be something like, I don't know if you watch Big Bang Theory, you can be those physicists, but I have never met a Nobel laureate who was not socially acceptable. They are very good human beings. So you're very young, don't push yourself. Once you get into your third year, that's the time when you actually start speaking of speed in that marathon. Then you have to prepare your legs that, okay, I have to go for a sprint. First 3 years, understand what is happening around you. You are too young to become a theoretician. Maybe I'll tell you, maybe 3 years later, I'll talk to you and you are an experimentalist. There is a very good probability. So don't say that I'm a theoretician. Say I like theory. It's okay. You're very young, and keep yourself open, because as soon as you say that I'm a theoretician, I want to be a theoretician, you close out an entirely big field in your life, which is experiment. I mean, I'm a nuclear scientist by profession, and NIT does not have a nuclear physics course. We just read nuclear physics for one chapter, but I'm a professional nuclear scientist today. I learned this entire thing during my first year of PhD. It took me 1 year to become a nuclear physicist. I did not push myself. I did not panic. I was ready. I was hungry, so I ate it all. So don't push yourself. Just chill out, I would say. And don't bunk classes. Yeah, I did not say that.
Yes, sir. That's the reason I'm here, sir. Like, I didn't want to make that mistake of not
Okay.
exploring.
Yeah.
But after the course, what are the opportunities for us, sir? Like,
Many. Well, so this is also something I can answer. Mohit's question also comes to my mind. So, opportunities is something which is extremely abundant. You will read the news probably that there are no jobs, blah blah blah. There is not this, there is not that. But if you're good at what you do, you will be hired. This is the bottom line. So, you wake up, you put this on your wall, the wall that you see opposite your bed. If I'm good at something, I will be hired. So there are extreme number of opportunities. One very simple way to explore these is our internships. You should do many internships. You should spend the part of your summers and your autumns doing internships. So, for example, I did. I think in my time, Raisa sent me to PRL once, the Physical Research Laboratory in Ahmedabad. That was an autumn internship in December. Then I went to Cern, and then I came to VECC, which is the Variable Energy Cyclotron Center in Calcutta. And as I mentioned, all this time I had a job in Infosys. I did not even want to become a researcher. And I went to Lindau, and then life changed. So I had a job. So that was one opportunity. I could have taken that job. Many of my friends are doing very good in their job. Many of my friends are in the defense forces. They're doing very good there. Many of my friends are into academia. They're teaching. They're doing very good there. So you should not think about what opportunities you have. You should ask yourself, what do I have to give them? You should basically ask yourself, why should they, if I am a faculty member, why should I give myself an internship? Once you answer yourself that question, that okay, I have XYZ skills, hence I should get an internship, then you will see life is much simpler. So you have to look at life from the other side. You cannot look at it from this side. You cannot panic that what are opportunities maybe generally in India, because we are a developing country. And since you live in Gujarat, no offense, but Gujarat is a very fast state. It's very fast and everybody is progressing.
Karnataka, actually.
Yeah, exactly. But NIT is in there. So, I mean, I have lived practically my whole life in Gujarat. So, if I come to Calcutta, it's a very slow life over here. So that also depends. So it might make you panic. It might make you think that, okay, I'm already 18. By 23, I have to earn money. I might have to send money back home, this, that. And then you end up panicking. Don't do that. So first year, second year, ask yourself, how can I do some skill development, soft skills development, hard skills development? You have to enrich your CV. Basically, you have to learn new things. You have to, if you are into theory, you have to have a very good hand on coding. You have to learn coding. If you are into experiments, you have to have a very good acumen of basic things like engineering, drawing, mechanical structuring, these basic things. So this is the time to do those. So now is not the time to worry what opportunities you will get. Now is the time to worry why should they hire you? This is the time to ask you that question and fill yourself with knowledge as much as possible. Then you will see, you will find, and then you will not even remember that you were worrying about it in the first year when you reach the fifth year. I can promise you that.
Thank you, sir.
No problem.
Hello, sir.
Yes, Mahir? Mahir, I cannot really hear you well. Could you speak up?
Actually, people have posted their questions in the chat box, so you can answer.
Okay. Sorry. Oh, wow. Oh, wow. That's a lot of questions. I'm sorry. I did not even see that. Thanks, dear sir. Okay. So I don't know, Bhavya, how much time do I have? Aditya, Bhavya, anybody can tell me? Deepak?
So, as much ever time you can
Okay.
afford.
Okay. So I'm at home, so I'll have to go sometime soon. So I'll just quickly go through the questions. So, okay, the first is Ishant asks me, can you please tell us something about your time in Cern? Super. They pay you a lot, first of all. They pay you 90 euros per day. And when you're 22, that's all you want, very honestly. And then you go to work and you have the Alps right in front of you, snowy mountains. So the first week just goes in that. You don't do any physics. If anybody tells you that I went to Cern and I did physics in the first week, that person is lying to you. You cannot do physics in the first week. Cern itself is so beautiful. So you have to actually adjust. You have to pinch yourself. You have to understand that, yeah, I am in Cern because there are 1,000 applications which go to Cern and they select just 2 people. At least in my time, they used to do this for the summer internship. So you have a probability of 0.02% to get into Cern, basically 2 out of 1,000 applications. And those applications are from IIT Bombay, all IITs, all ICERs, everywhere. So there is a little luck factor, but yeah, you have to be smart, as I was mentioning to Rohan right now. So you have to enrich yourself. So I had enriched myself, and I was ready. So when they saw my CV, they said, "Okay, this is the kind of person we want to hire." They hired me. The time is beautiful because in CERN, even if you're 21 years old, they treat you like you are 30 years old. In the sense, they don't treat you like a kid. So you go to work, you're given an assignment, and that's it. You have to do. You have to figure out how, you have to figure out where, you have to talk to people. So my supervisor told me, he was a Bulgarian guy. He told me that, okay, we'll push you in the ocean and we'll see whether you can swim or not. And if you're not able to swim, you don't belong to CERN. But all the cases, they swim out. Some take 1 week to swim, some take 2 weeks to swim, but people are always able to survive. So the time in CERN is nothing like you will have in any place, especially if you're going at an age as young as I was lucky enough to go to. But what it does is it prepares you for the future. It tells you there is so much out there in the world. You have to wash your clothes, you have to cook your food, you have to manage your time schedule, you have to attend classes in the morning. So everybody thinks CERN is CERN, but I'll tell you the schedule in CERN. So You have to wake up at 8 in the, you have to wake up at 7 in the morning because at 8 we have lectures. So we have 4 hours of lectures. The Nobel laureates and Cern scientists teach you. You have to learn everything from atomic physics to high energy to quantum mechanics to classical, everything under the sun. And then from lunch hour, you get 1 hour lunch. And from 1 to 5, you have to work in the lab. And this goes on for 60 days, more or less. 4 hours of lectures, 4 hours of lab, 4 hours of lectures, 4 hours of... After 3 weeks, you are like, yaar, ho gaya Cern ka nasha. I've done it. I want to go back home. So, things sound funny, things sound, fascinating when you read on people's CV, but there is a lot that goes on behind that we don't write in our CVs. It's as simple as that. So life in Cern is beautiful. Time you learn a lot. I mean that goes with that comes with the package. You meet many scientists. You meet your age group scientists where you see, I still have friends from Cern in my colleague circle. You learn so much as to what people are doing, who is doing what is happening where. There's so many opportunities. There's such a good culture. Every evening after 5, there is a cultural evening in Cern where people just have drinks and organize themselves, meet each other, play games. So it's beautiful. Okay, next question. I just wanted to ask, what do scientists actually do? Like make models or like, that's a very, very broad question, Anuja. It depends on what field you're in. I'm a nuclear physicist. I'll just keep it short. I'll tell you about myself as I was mentioning to others as well. We are 3 kinds of nuclear physicists. We either do simulations, or we do theory, or we do experiments, basically. And as I was mentioning to Ram Kumar, we 3 work in very good coherence, and we all try to achieve the single goal of doing nuclear physics, trying to understand what the world is made up of, nuclear astrophysics, what is happening, and then basically we have theories which predict things. Experimentalists are the ones who are responsible for achieving those goals that theoreticians have set forward, and simulation guys are the ones who tell us what we can do and what is our scope of doing. So if I want to put huge detectors, he will say no, it doesn't work. So basically that, and modeling is a work which is basically done by theoreticians. They do physics modeling basically to put in calculations and to see single particle models, bosonic models, and to see how they can push the boundaries and see what nobody else has seen. Aditya, okay. Aditya is the one who contacted me first. I came to know that you. Well, no, I did not actually. So CMS is a huge experiment. It works with around, I think, 3,000 people or something like that. If you look at a publication of CMS, the first 3 pages of the paper are just names, and even then they don't complete 50%. So my work basically was to develop a cosmic muon stand for the CMS experiment. So what I did was, it was very simple physics-wise, but it was very challenging experimental-wise, and that is exactly what I wanted. So cosmic muons, if you have read, they penetrate everything. They were formed during the Big Bang. They are still traveling. They will keep on traveling until the universe collapses, and maybe even after that, muons will be there. So in high energy and nuclear physics experiments, what happens is you have detectors, and detectors are basically solid materials, right? So whenever a muon hits your detector, it gives you a signal. It gives you a pulse, basically, and that pulse is that readout is a scintillator and a PMT. A scintillator is something that scintillates, fluorescence, and a photomultiplier tube is basically that takes the light and converts it into electric current, electronic signals, basically. So what we were facing is, we would see there's a lot of noise. Even when we were not running an experiment, we would see our detectors were always reading something. And then we saw it, we knew that it was muon. So my task as an intern over there was to design a stand in a way that it was a veto. So veto works in this way. So you have detector A, you have detector B. So you tell your detector B is your main detector, your physics detector, let's say, and detector A is your veto detector. So you tell the veto detector to read all the muons, and then you tell detector B to read when detector A is not reading. So you run them in anti-coincidence with each other. So it's not very 100% proof, because 100% effective, because muons, the rate is very high. So what we try to do is, we try to tell detector B not to read when detector A is reading. So it does not read the muons. It gets the muons, but it does not read them. So this was my basic work at CMS. But I actually have a project report I can actually share with Physics Club. I would be more than happy if you want to read and see what I did 9-10 years back, probably. okay, what is the current status of Tokamak concept? And no, I'm not an expert in this, and I have a habit of not commenting on things I'm not an expert in. I'm sorry, Harsh. I'm way far away from. So this is also one thing that we feel when we are young, that okay, I am a nuclear physicist, so I know things about reactors. And no, Tokamak, it's a huge concept, and it's a completely vast, is a completely different thing. Well, but I can tell you gossip. Uh, yeah, there is some fusion thing happening. If you read newspapers and things, we have turned a corner, because I have friends. As I said, you should have interdisciplinary friends. So I have a lot of friends from interdisciplinary areas, and they tell me, well, the main question was storage, and they might have done something in the storage area. So there might be a Nature publication coming sometime soon in the next year or something. And well, you never know. And to tell Mohit, you see, Tokamak, there is something still to be done. So you can still do something over there. How do you get all the things, Pooja? Money. So this is one big reason I left India to do a postdoc, and then I got employed as a research scientist, because to be honest, India is a bit short on money, and the equipment that we play with, they are extremely expensive, and the reason they're extremely expensive is they're extremely new. So I basically myself am responsible for inventing different types of detectors, and when I, as Akash, invent a detector, I do one piece. So if you at NIT Surat want to have that, I will tell you, you have to order minimum 1,000 pieces, because that one piece of detector has to go through an industrial processing and industrial manufacturing, and that's an extremely expensive chain. So unless people like you, people from Japan, people like from France, Italy, everybody is not asking for my detector, I will just make one piece or five pieces, whatever is required for my case. As soon as I see that the demand is at an industrial level, then the price comes down, the production price comes down. As with everything, if you want to make one exclusive thing, it's very expensive. But if it's common, it's cheap. So I get all my things because we have money. So we have a lot of money. That's a fact. And this was one big challenge in India. Yes, Pooja?
Actually, I asked is because I was a fresher and I didn't know anything about it. But now I
Mm-hmm.
know I still have to wait to reach the college yet. We
Yeah, yeah,
haven't even visited the college, so
yeah,
I'll wait
yeah,
for it yet.
yeah, surely. But yeah, as I was mentioning to your colleagues as well, if you have the knowledge, places with money will hire you. And for this exact purpose, I recently wrote an article for Squash. I don't know if there are Squash members here. You can have a read when that article comes out. That is actually to what not to do while choosing your career. And that is one thing. You should not run behind money at this stage. You should take it slow. You should gain knowledge. I did my PhD from the Delhi University, by the way, and there was no money in Delhi University. Absolutely, we do not have. I mean, it's a typical government university, and we do not have. There is money, but we don't know where it is. I mean, nobody knows where to get the money from. If you send a purchase order, that takes 6 months to get processed, and you have forgotten what experiment you wanted to do. So if I had to make a cable, I had to go to Chowri Bazaar by myself. I had to buy that cable. I had to get the connectors. I had to solder it, test it, and then I can use it. So, and now I'm in GSI. I just click, and I have 100 cables on my table. So you cannot be demotivated because you don't have resources. You will have resources. You have to just think about knowledge. Darshil, I have analytics and business generation to different field. What can I be? Well, you should not. You should always be an observer. Every good experimentalist, Darshil, is first a very good observer. So these are not very different things. As you mature, as you stay in the field more and more and more, you will see observation and research are very similar. Research is 99% about observation, and well, not 99%, I would say 70% observation and 30% inference. So it's very good if you have a random project and you wanted to go somewhere, and you wanted to go to Delhi, you ended up in Calcutta. Very good. This is what it should be. This is what I was telling your colleagues. So this is exactly what it should be. You should not focus too much on a project, because then you become tunnel visioned. And at your age, until you're 25, 26, don't be tunnel visioned. Grasp as much as possible. If a project takes you want to go from A to C, but it takes you from X to Z, go. Just go. Maybe you like it better. As I told you, we did not have a nuclear physics course in our semesters, but See, I'm a nuclear scientist, and I did not worry about it, so it will work. Jyoti Raj asks, well, what are the opportunities in CERN? I think I've answered. And knowledge, well, skills and knowledge are very common set. So CERN really likes people who want to do hands-on things. They also hire theoreticians, they also hire simulation experts. But my personal experience tells me that your probability to go to CERN increases if you have a very strong internship before you apply to CERN. And I had a very nice internship at PRL where Ajay Rai sir basically arranged that autumn internship for me. I did not even apply for it; he just sent me there um, in the winter months, and that really helped in my application at CERN. So there is no trick book to apply to CERN. Very honestly, I can tell you 20 things to do. I mean, after me, many people have applied to CERN. They have taken my CV, they have taken my recommendation letters, they have applied as it is. Unfortunately, they could not crack it. Now I basically sit. I work closely with CERN even now in their isolated experiment, and I talk to people who filtered these applications. It's kind of a luck factor because you have to be at the right place at the right time, as with many things in life. But it's not 100% luck because you can be at the right place at the right time and not have the skills. So you should have the skills. You should have some hands-on experimental skills, and then wait for the right place and the right time. So when it comes, you're ready, and they absorb you immediately. So that's what I can advise you: be in the lab, work, get your hands dirty always. If you're leaving a lab and you can eat with your fingers, you have not done a good lab. You should do a lab when your fingers look actually dirty. You should really focus. Uh, Jignesh, no. There is nothing to do if the deadline is passed. CERN is a computer. CERN is not somewhere you can, telephone somebody and say, "Sir, my application accept kar lo." It doesn't work that way. So you just have to wait for the next year, unfortunately. But yeah, you should be aware of these things. You should have your application ready. You should have everything prepared. And when next time when it comes, if you have the skills, you should immediately go for it.
So I am
Opportunity.
from first year student, so
Mhm.
re- I apply for next second year.
Well, it's very difficult for you to get into CERN until you're in third year because they expect some kind of, because they don't want to really it's not a tiny tot school. So they don't really want to hold your finger and tell you to do everything. So they want you to have some kind of experience, not extremely big experience, but as I mentioned, you should aim for two solid internships, solid in the sense very good internships before you apply to CERN, because the competition is very high. It has always been very high, and now it's even higher because the population is increasing in the world. It's as simple as that. So first year it's very early. I will not discourage you. You should always apply. Maybe you get through. I would be very happy if you get through. But I would advise, but you should also try to get some other internships at the same time so that you don't end up wasting 1 year betting at CERN, basically.
Excuse me, sir.
Yes, Rohan.
Sir, could you suggest some internships, sir? Like to
It depends. So very good internships happen at PRL, Physical Research Laboratory, Ahmedabad. That is one thing you should go for. There is also something sponsored by the NASI. It's called an IAS, Indian Academy of Sciences internship. Very good internships. You should apply that. I recommend everybody to apply for an IAS internship, but you should be very aware of, very mindful of the deadlines and everything. And IITs, write to your professor if you want to do. And IITs are very flexible in this because they are very welcoming, I've seen. If they have a slot open, they will just call you. But very frankly speaking, if you want to do very good physics, if you have a very good idea, you don't even need to leave NIT. You can do it in NIT itself, in Surat, NIT Surat itself, because there is nothing that our department does not have at this point in time. You have very good mentors, you have very good facilities, you have a lot of money flowing around, so they can buy things for you, they can help you with resources. So if you want to do very good internships, why don't you just do it at your NIT itself if you don't find it anywhere else in that sense? And even if you find it at anywhere else, because our institute is very competitive, our department is very competitive, it has a very good reputation uh, in the global stage, I would say. Ricer, for example, collaborates with FAIR-GSI. Vipul sir collaborates. Devesh Roy sir collaborates. There are many good collaborations in the institute itself. You don't need to go very far, but yeah, if you want to go, IAS is one, PR is the other. To name a few, IISc, you are in Karnataka, Bangalore. Go to IISc Bangalore. There are very good people working there. Write to IIT professors. First, you have to think why you want to do an internship. Then you have to think what you want to do it in. Then you have to apply for it. You cannot just say, "Sir, I want to do an internship. Please take me." Then your emails will never get replied to, which very often happens. Aditya says, "Okay, I'll try to keep it very quick now. I would argue theoretical physics is boundless. Only." Okay. Yeah, well, that's true actually. The biggest experimental physics limitation is actually money. People don't talk about it, resources. But I would tell you, Aditya, with the way theoreticians are working, they also have a very big problem in computational power. Many of my theoretician friends, they cannot run their models because they're so heavy. It takes them months to get results out. So you also have some, some restrictions now, because you can imagine many things. You can look at a very prominent theoretician in India, Ashok Sen. He works in string theory. He will never get a Nobel Prize. He got the Yuri Milner Prize 6-7 years back. He got every prize. They want to give him a Nobel Prize, but they cannot give him a Nobel Prize because his findings cannot be proven by an experiment in the near future. That is unfortunate. The way Peter Higgs got it with his colleague, because Cern actually found that. Otherwise, Peter Higgs would never have received a Nobel Prize. So theoreticians have a limitation. You are a bit far away from Nobel Prizes than experimentalists. We are closer to Nobel Prizes, I can tell you. If you look at the percentages, we are closer. But yeah, you are right. I'll tell you, experimental physicists can also be very imaginative. I mean, we make detectors all the time, and they are brilliant. We use diamonds to make detectors. You will, things that go in the International Space Station. We recently from GSI sent a detector to the Mars, to the planet Mars. Basically, it's with the rover. It's a gamma detector. We can be very inventive. So I will not agree with you. We have many limitations. I think we both have many limitations when it comes to resources. Jyoti Raj, my LinkedIn account is open, I think. I just added, I think, Bhavya, I added you yesterday. I sent people friend requests from my side. So my LinkedIn is my name, Akashrup Banerjee. You can just take it from your colleague. What are the efforts I've done? Well, a lot. As I mentioned, I did not study nuclear physics in my 5 years. I was more into electronics. I loved working in Vipul sir's lab. I did my master's dissertation with Ajay Ricer, but I used to spend a lot of time because my friends used to work in Vipul sir's lab. And as often is the case, you want to be where your friends are. So if you have worked in Vipul sir's lab, you would see a high vacuum chamber. I know everything about that because I used to work with that a lot. And then I went to Delhi University, where I wanted to work in this project with detectors because it was something new, and I had to spend 18 months like a child. Basically, I had to study everything from zero. I used to study. I would study from my 10th or 12th exams, and there is some hard work. You have to spend at least 4 to 6 hours reading books, reading research papers, because you have other things as well. You have to propose experiments. PhD has to be completed without time-bound state. So it is hard work. It does not scale. I was in Delhi University, so I also contested elections there and everything. So it's not like you have to become a dull person. You can do everything, but you can still be good at what you're doing. So you just need to balance your time. You need to be relaxed. You need to be chilled out. I always tell everybody, don't panic. Take it easy. It will be done. Okay, thanks, Disha. This is a compliment. How to read research paper faster, efficient? That's a very good question. Actually, to do when I was in my first year. You should take a research paper. You should read the abstract. You should read the result, and then you should leave that research paper alone, or maybe just read the experimental method section, and then just leave it alone, and then see if you are able to join the dots. So a paper is basically an abstract, introduction, experimental method, result. telling you to do, I'm telling you to read the first section, last section, and maybe the middle section. Then you have to think in your brain whether you're able to join the dots. And then you read the paper. Then you see how wrong you were or how close you were to what they actually wrote in the paper. But this comes, you cannot start reading papers fast to begin with. You read them slowly. You have to first understand how is research paper written. It's an art. It's like cooking, you know. There are many ingredients which come in sequence. If you mix up the sequence, your food is messy. Like I cook these days messy food. But research paper is like that. You have to be very, very patient about it. You cannot force it. You cannot force it to be fast. When you were learning to walk, you did not want to run, right? You first took baby steps, and now today you can run. Research paper is very much like that. You have to understand what you're reading, and then you will see. But what helps is if you have a register with you. You make a logbook kind of thing. You read the research paper, you write the research paper title, you write the authors, you write down the abstract. Because when you write, your brain accepts it faster. This is my personal experience. Maybe there are other techniques, but there's no shortcut. There is no shortcut in science, unfortunately. That's the fact. There's a shortcut in life to be true, but especially in physics, there is no shortcut. I've tried taking those shortcuts, it did not work out. So don't ever try. Okay, so Deepak asked me, well, as I said, you don't need to be an experimentalist in a lab. You have to be a very good observer. And when you're a very good observer, you have everything in your personal life. You analyze everything. You become more patient. That is one thing I can tell you. I mean, if somebody met me in 2010 and if somebody meets me in 2020, the first change that I'm very confident that person would tell me is, I'm very patient now. And research makes you patient, which is very important. You have to take things slowly. You cannot rush with life. You cannot rush with things. You have to take things when they come to you. It's as simple as that. And it helps. Research helps. It develops your personality. It develops your acumen. When you write a paper, for example, when you present papers in conferences, you know how to interact with people. You know how to present in big audiences. When you can do that, you can tackle life. Because at the end of the day, you have to live in a bungalow or a flat within a society, and you cannot close your door, and you have to talk to your neighbors nicely. You have to do everything nicely. So research teaches you that. It prepares you for life, in short. Will you do another session related to intern? I could, but I'm on vacation, and technically I'm a German employee now, and we take our vacations very seriously. So I might not be able to do it this year, but I would be able to do it next year. But I can also recommend many good, better people than me, who have done more internships than me, who know more internship opportunities, to do another session, and they would be more than happy. And what I always wanted, I was talking to a few seniors of yours who have passed out NIT now. I'm very happy this physics club is there. Maybe if you have a website, I've seen you have a Facebook page, you should actually make a list of these internship universities and then pin it on the top of your page, make it your cover picture or something. And you can just, so somebody wants something, they come to your page, they know what internships, and it will take some work, I agree, because the deadlines will change and there are many internships in the country. So if you just put, for example, Cern deadline January, IAS deadline March, PRL deadline October, so people get very good ideas of, okay, this internship is this, and this is the time frame, requirements are these and that. So this is helpful. So I'll take this last one. What was the internship at PRL? It was scary. So the topic of my internships was introductions to the basics of quantum mechanics. And I was doing my internship with a very, very serious person. His name was Naveen Mahajan, I think. And incidentally, he was also colleague of Riser. So I had some very good interactions about him. And it was not very useful because I was in a 3-week internship at PRL. So it just came and went. But what it did was it told me what an internship is, first of all. It told me what is expected of me. So my idea was like, I go to a person, he tells me, okay, Akash, do this. So on Monday you do this, Tuesday you do this. So this was my expectation because I was in institute and everybody used to tell us what to do. When I went to an internship, I realized that, okay, they want you to think. They want you to think. And then it was good. It was short. It was 3 weeks. Actually grasp. I mean, the only output of that internship was it introduced me to internships. And then I understood the seriousness of it, the seriousness, but the sincerity of internships. So everybody that you're here, you should try to do internships, even if it is at NIT, and do them sincerely. You don't need to do them seriously. Do them sincerely. This is a very big difference you need to understand in science. You should not be serious. You should be sincere about your work. Because if you're serious, it will get stressful. Be sincere. Be happy about what you're doing. And one additional thing, don't run to faculty members for recommendation letters, because everybody's going to do that. And you have to do what other people are not doing. You have to learn skills. You have to work in a way that a faculty member wants to write a recommendation for you. So you have to do efforts. As I said, there is no shortcut. But the real route is not that difficult. I could do it. Everybody could do it. I'm not extremely intelligent. I'm not extremely smart. If I could do it, everybody can do it. And you have to go through the procedure. That's it. Yeah. Did I take a question?
Akash, I have a question.
Yeah, I think.
Yeah, it's about the basics. Like in nuclear physics, we talk about radioactivity decay, and it's clearly mentioned. Like when we study about it, it's clearly mentioned that no particle, we can't expect that particle to decay in certain amount of time. It's a completely random event. So, but if we can do that, if we theoretically or experimentally come into a conclusion that when a particle can be done, won't it be more efficient?
Well, first I can give you a lecture on this topic. I don't think this platform is because I'm a professional in this. I don't think you want a lecture. In short, what you're saying is yes, it would be, but do it. That's the challenge. Nobody has been able to do it yet. So we have alpha decays. So we consider alphas and betas as particles, and we consider gammas as radiations, basically X-rays, gammas. These are radiation categories, basically. In short, the challenge is the energy. But it's a very specific question that you have asked, and I think I will bore the other people to death if I start talking about it. But the challenge is the physics of it. When you talk about emission of a particle, there is a process happening inside an atom or a nucleus which leads to that emission. Now you have to understand whether that emission is suitable or not, and that will answer your questions. But it's a very, very, very interesting topic to do a research in, and you will learn a lot if you try to do the mathematics of it. And the mathematics is extremely tedious, because when I say you have to understand how a particle left an atom or a nucleus, what I just did is I told you 3 years worth of quantum mechanics in one line. So it's very interesting what you're saying, but it has to be done. And I would be very happy if you start reading books like R. Shankar or Kenneth Crane, books like those, and you will understand what are the practicalities, what are the challenges in such kind of theoretical predictions, and why people have not been able to see this. Nuclear physics is very young, 60, 70 years old, to be honest. Nuclear physics, radioactivity is 100 years. So it's a young field. You can do something new. Okay, I have one more question, Ashwini. You don't know where you start actually. You just do it. You take these little steps, as I mentioned. Yeah, you take these baby steps. You don't want to become an experimentalist. You see what you want to be first of all. As I was telling Rohan, there is a very, very finite possibility 3 years later he will turn into a pure experimental physicist. He will completely leave theory and go. So you don't want to become something. You don't really, what I did not do it. I did not fix a goal, and I just took everything and I saw what I liked. It's like going to a fair, fun fair, going to a mela. You go to every stall and you see kahan kya bik raha hai, and then you see, okay, I want to buy this thing. So internships help you do that. You actually go through these experiences. You see that, okay, what do I like? Do I like this? This internship was not so good. This was better. Okay, maybe I like this more than that. then you actually prime yourself, then you actually warm up yourself for that, and then you will not even know when you actually enter the field. Preparation for an experimentalist is observation. You have to question, you have to ask questions. Now, I don't tell you to question your parents or your faculty members, not that, but you have to ask questions about the phenomenon, about the things that are happening around you. You have to ask, you have to start with very basic questions. You might think you know, but when you read, you will obviously learn one more thing. I mean, start with something as basic as internet. I don't know how many of you know that the internet that you're receiving right now runs under the ocean. There are huge cables running under the ocean. Now, I tell you this, now it should raise a question in your head. What did that guy just said? Under the ocean? Go to the internet. Search about the internet. That how does it run under the? Who lays the cable? How do they repair the cable? What happens? There must be so many things. How does the internet reach your home? What is the concept of bandwidth? What are these things that you have a mobile phone, super high-fi technology, semiconductor technology. You learn and learn. You read, you observe, and then one day it doesn't happen one morning, but one day you think that yeah, I like the field, and then you actually start developing a very good interest for the field. So there is no shortcut, but don't panic if you want to become an experimentalist, but you're not becoming an experimentalist. Don't panic. Keep your interest alive. I've told you, I've seen 60-year-old theoretical physicists turning into hardcore experimentalists. 60 years. So they were ready, they liked it, they started doing it. So no hurry, yeah? No rush. Good. I don't see any more. So I think I took most of them.
Yeah, so first of all, thank you, sir, for this amazing, fantastic talk. I guess most of you would have gained new insights and found this useful, like me. Uh, Thank you. I want to convey my sincere gratitude to Dr. Akashrup Banerjee, sir, for taking out time for us. I want to thank Dr. Ken Pathak, sir, our faculty advisor, Ajay Kumar, sir, for introducing you, and a big thank you to all the participants for keeping this session interactive with your questions and queries. And until next time, thank you all. Stay safe and bye.
Thank you for organizing. Thank you. See you all.